Hello and welcome back to Calculus. This right here will probably be the last video then actually of all of the curriculum. So this will be on finding the polar equation and how to apply calculus into all of that. So there are three topics that we are looking at for today. The first one will be to solve for the equation of the tangent line. And then the second one will be finding the area between curves, and finally the arc length. So basically all of these things that we've dealt with in the past, but except this time we're applying it to polar equations then. All right, so let's go ahead and get started to see how this actually works out. So in the first example over here, we're given the polar equation r is equal to 6 plus 3 cosine of theta. And what I want to do is I want to find the equation of the tangent line that passes through where theta is equal to pi over 2. So geometrically, what that means is at pi over 2, so that means we're going to make a rotation over here. And that right there is going to be theta is equal to pi over 2, which is equivalent to 90 degrees. At that position, there is a point that it goes through the curve. And what I want to do is I want to find the equation of that tangent line that is located right there. So, pretty typical Calc 1 question for the most part. So thinking about Calc 1, then what I need to do is I need to show the following, or I need to solve for the following. I need to solve for what is dy dx, because that is what the slope is always represented as. Now, keep in mind that we're in polar form, so that means that we know the following. R times sine of theta, that's equal to y, and then x is equal to r cosine of theta, and that's equal to x then, okay? So those two equations, what I need to do is, again, then solve for dy dx. Well, the best way to think of it is this is kind of like the polar equation. The setup of it is kind of like the parametric equation. So what that means is I need to solve for dy d theta, and also I need to solve for dx d theta. So kind of like dy dt and dx dt. Okay, so here that's what I did underneath over here. Okay, so the first part dy d theta. So taking the derivative with respect to theta, the right hand side I am going to have to take the product rule. So be very careful, because theta is a variable and r is also a variable, because both of them are kind of like, they're independent time variable with respect to the parametric equations. So by product rule, then it's going to be the second equation, which is sine of theta, multiplied by the derivative of the first with respect to theta, so that's dr d theta, and then plus r, the first equation, multiplied by the derivative of the second equation, sine of theta, which becomes then cosine of theta. Okay, remember, taking the derivative with respect to theta then. Okay, so that right there is going to be my dy d theta then. Okay, now we're going to go ahead and do the same thing for x. So for x, we're going to take the derivative and solve for what dx d theta is equal to. And by the product rule, then it's going to be equal to right here. So same thing. So cosine of theta times dr d theta plus r times negative sine of theta then. Okay. So once we have dy d theta and dx d theta, well, we think back to, okay, what we did with the parametric equation, which was, okay, I will go ahead and divide one by the other, because that's how we're going to introduce dy dx. And by doing so, that is what's going to allow me to solve for dy dx. Now, we know what theta is equal to, which is pi over 2. So there are some components that I'm going to need to solve for along the way. Because if you look at the equation for each one of these, right, I know what theta is, which is pi over 2, which is great. I don't know what r is, so that is something that I need to solve for. And I don't know what dr d theta is, so that's also something that I need to solve for. So let's go ahead and do that on the side right now, okay? In order to solve for what r is equal to, I'll probably just go ahead and plug it into the original equation. So it's kind of like saying, if you know what x is, how do you solve for y? Well, you plug it into the equation then. So if I plug theta is equal to pi over 2 into the equation of the polar, then I'm going to get 6 plus 3 times cosine of pi over 2, which then is equivalent to 6. So that right there is the first part of it. So r is going to be equal to 6 then. Now for dr d theta, then that means I just need to take the derivative of my equation. So let me go ahead and do that right now. Take the derivative with respect to theta. So dr d theta is equal to negative 3 multiplied by sine of theta then. Okay, so now I do believe we have everything that we can go ahead and plug in. And keep in mind, even though there's theta in dr d theta, that's fine, because I know what theta is equal to, which is pi over 2. All right, so let's go ahead and solve for each piece then. So dx, actually, let me go ahead and change the color of the pen. So let's start with dy d theta, right? And we're going to plug in the point, which is going to be 6 comma pi over 2. And keep in mind, this right here is polar, okay? So this right here is polar. So if I plug in 6 for r, and also theta is equal to pi over 2, and wherever I see dr d theta, I'm going to go ahead and plug it in. Then we'll get our answers numerically. So first off, sine of theta, so that's sine of pi over 2, so that's equal to 1. Multiplied by dr d theta, that's negative 3 multiplied by sine of pi over 2, so that's also equal to 1. And then plus r, which is equal to 6, and then multiplied by cosine of pi over 2, which is equal to 0. So cleaning that up, we are going to get negative 3, it looks like, for the most part. Okay. All right, now we're going to go ahead and solve for dx d theta, right, and doing exactly the same thing. So I'm going to go ahead and plug in that same polar point, which is 6 comma pi over 2. So that is going to give me numerically cosine of theta, so cosine of pi over 2, that's going to give me 0. And it doesn't matter what dr d theta is, that is just going to be 0 nonetheless. So cosine, 0 multiplied by dr d theta, and then plus r, which again is equal to 6, multiplied by negative sine of theta. So that is going to be negative 1 in this case. Okay, so that gives me, looks like it's going to be negative 6. So put these two together. The result is that you get dy dx, which is going to be equal to, looks like it's going to be 1/2. And definitely looks like it's going to be 1/2 in this case. All right, great. Now that we have the slope, we need the coordinate. And the coordinate, now this is where you have to be careful also. The coordinate, we need to kind of convert it back into Cartesian because, well, it's the equation of a line, right? So what I need is going to be y minus y naught is equal to the m multiplied by x minus x naught. We know the slope, that's equal to 1/2. The coordinate over there, if you look carefully, remember my polar coordinate, which I normally write it as using brackets just to make it a little bit more easier to recognize that it's polar. We need to convert that back into Cartesian. And from there, you can see the picture is supposed to be 0, comma 6 right there, right? And another way of solving for it, if you don't know it, is that x again is equal to r cosine of theta, and then y is equal to r sine of theta. You can plug in r is equal to 6 and theta is equal to pi over 2 in order to figure it out also. But nonetheless, we have all of our components, and then now we can just go ahead and finish it off. So y minus 6 is equal to 1/2 times x minus 0. So my equation is going to be x over 2 and then plus 6. So it definitely looks like it's going to match up then. All right, cool. So that right there is how you get the equation of the tangent line. So probably good to solve for each part individually, plug it in, and then afterward get the numerical value, okay? Next, what I want to do now is find the area of the region in the first quadrant bounded by that curve. R is equal to 6 plus 3 cosine theta. So once again, we have the same curve right here. And what I want to do is I want to find what is the area of that curve within the first quadrant. So that means it's going to be this piece over here, and all the way over here, and so on and so on and so on. Okay, so there it is. All right, so now let's think about how the area is going to work out for polar equation. In Cartesian, what we did was, in order to solve for the area underneath the curve, was we created partitions that are rectangles. So here, for example, let's try to draw it on the side. Your partitions would look something like this. So those are going to be your partitions. If it were like X and Y, Cartesian once again. And then from there, we said, okay, well, the area underneath the curve is going to be y dx then, okay, from A to B for x. Now, for polar, the setup is going to be a little bit different because your polar, remember, your two variables are in a different orientation, right? You have r, right? So let's say that here is going to be the origin. You have r, which is over here, and then you also have theta that's over here. So those are your two different variables. They're not horizontal and they're not vertical. So the question is, okay, well, how do you figure out what's the area then using these two orientations? Well, the idea is still the same where we're going to create partitions, but our partitions are not going to be rectangles, but instead they're going to be wedges of pieces of a circle. So here, just to give you like a illustration of it, then the small little wedge is going to be something like this then, okay? Where we're going to try to find the area of this small little piece, okay? And then what we're going to do is we're going to say we're going to add up all of those areas, those small little pieces. So that right there is going to be one partition. And then I guess if I wanted to, I can go ahead and move to the next partition, which is going to be a little bit higher up. And then that right there, that's going to be a partition. All right, so let's take that wedge out. So then that way you can kind of like see how this actually works out. There's a fast way of representing how this all works out, and I think I want to go and do that because otherwise the explanation might take a little bit too long. The best way you can think about how to solve for the area of the wedge is the following then. Let's go ahead and say that this right here, this piece, we're going to go ahead and call that delta theta because it's a small little change in theta. The R value right there, that is going to be the radius. Now, the area of a small little wedge inside a circle, right, if you remember, is supposed to be 1/2 times pi r squared. And then if you want the area of a small little wedge, what we'll do is we're going to go ahead and multiply by that wedge right there. So it's going to be delta theta and then divided by 2 pi. So that right there is going to be the area of the small little wedge right there. And if, I'm sorry, there's no 1/2 here. I'm sorry about that, okay? And then if we clean that up, you'll notice that the pi's are going to cancel out. So then that means it's going to be 1/2 r squared, and then we have delta theta. Now, I want the sum of all of those pieces. So that means that the total area is going to be the summation of all of those wedges. So the summation of 1/2 r squared delta theta. And immediately, just like before in calculus, as soon as we see summation, and then we also see delta theta, then the result is that we have an integral. So the integral is going to be 1/2 r squared d theta, and then from the boundary of a to b. So there's kind of like the fast version of it. Now, the part that it's a little, you might be a little bit skeptical about this is some people might say, okay, well, this right here, I do believe, we call that R, that's totally fine. But then what's underneath it, well, that's going to be a little bit different. That's going to be like, R star or something like that. And so it turns out that if your partitions are small enough, then those two, R and R star, are going to be the same thing. And hence, that's why we can do that then. Okay, so in that way, you can kind of neglect the fact that it's going to be changing that much. But nonetheless, let's go ahead and use that equation, and I'm going to go ahead and put it on the side for right now, okay? So we're going to go ahead and move this over. So clean this up over here. And definitely this is one of those that's easy enough to memorize. So we're going to go ahead and, put it down as an equation as something that you need to memorize. So the area from A to B of r squared d theta, that's going to be the area for a polar equation. We know what R is, and we know what we know the equation R. So now we just need to figure out what the boundary is. So go back up over here, and remember, theta is a rotation from the 3 o'clock position to counterclockwise. So in this case, in order to cover all of the first quadrant, your angle of rotation is going to be 90 degrees. So what that means is over here, my area is going to be equal to 1/2 multiplied by the integral from 0 to 90 degree, which is rewritten as pi over 2, and then r squared. So that is going to be written as 6 plus 3 times cosine of theta, quantity squared d theta. So right there, that's the easy part. It's setting it up. Now, finding the area of it, so this depends on if you have a calculator or not. A lot of times you can solve for it with a calculator, but sometimes you can solve for it by hand definitely, and this is one of those cases. Okay, so 1/2 carries over. If I multiply everything out, we have the integral from 0 to pi. Expand all of these guys, that's going to be 36. And then plus, looks like it's going to be 6 times 3 times 2, so that's also equal to 36, times the cosine of theta, and then plus 9 times the cosine squared of theta, and then d theta. The first two parts I definitely can integrate because those are easy enough. But the second part, I think I'm going to have to use an identity to replace it, so then that way I can easily integrate it. So 36 plus 36 cosine of theta, and then we have plus 9 divided by 2 times 1 plus cosine of 2 theta. So that's going to be my substitution right there. And now everything is going to be integratable then. So it's equal to 1/2, and then we have the multiply by, let's go ahead and integrate, 36 theta, and then we have plus 36 sine of theta, and then the next part will be plus 9 over 2 theta, and then plus 9 over, looks like antiderivative, so 9 over 4 times the sine of 2 theta. So boundary from 0 to pi over 2. So plug in your upper bound, plug in your lower bound, and then we're pretty much all done. So it definitely sounds like it's easier said than done, right? Because, all the algebra work over here. Let's see. 36, if I'm going to plug in the upper bound minus the lower bound, that looks like it's going to be 36 multiplied by pi over 2 multiplied by, minus 0. So that's just 36 times pi over 2. And then plus, for the next part, it's going to be 36. And then we also have pi over 2 plugged in. That looks like it's going to be just 1. And 0 plugged in is going to give us 0. Next one is going to be 9 over 2 multiplied by pi over 2. And then the last part right here. Now, this part, you got to be careful. Sine, when you plug in pi over 2, that is going to give you, looks like it's negative. So that means it's going to be negative 1 over here. When you plug in 0, you're going to get 0 then. So there it is. Add up all of these, and then we're pretty much home free then, okay? So let's see. The first part looks like it's going to be 1/2 multiplied by 18 pi, and then plus 36, and then plus 9 pi over 4, and then we have minus 9 over 4 then. Okay, so we'll just go ahead and leave that as the answer because, we don't want to mess up, potentially get the wrong numbers for the answer, okay? All right, so now let's go ahead and move on to something a little bit more complex with the area, area in the curve, right? Let's say this time I want to solve for or set up but do not evaluate the area of the petal that is formed by r is equal to 4 sine 2 theta. So if you recall, if you have sine 2 theta, that composite value that's multiplied by theta, if it's even, that gives you double the amount of petals. So in this case, since there's 2 theta, so that's why there are 4 petals. But whereas if the number is odd, then it's just going to be that same number. But nonetheless, what I want to do is I want to solve for the area of this piece over here. Okay, I want to solve for the area of that one petal right there. And what we're going to do is we're going to set up an integral for that. Well, the best way to look at this is think about how theta is going to work. What is the, right now we already know that the area is going to be 1/2 multiply the integral from a to b of r squared and then d theta. We know what r is, so that one's easy, but we don't know what the boundaries are. Well, the boundaries is basically when r is going to be equal to 0 because look, I am bounded, according to this petal, I am bounded by where r is equal to 0, and then you're going to go all the way around to where the next part is when r is equal to 0, right? So essentially, in order to finish one petal, you have to go from one r is equal to 0 to another r is equal to 0. So best thing I need to do is, on the side, we're just going to go ahead and solve for that. 0 is equal to r times sine of 2 theta. Let's see, I'm going to go ahead and divide by 4. So that means 0 is equal to sine of 2 theta. And then where sine is equal to, where sine is equal to 0, that I do believe is supposed to be pi n. Every single pi, you're supposed to have a solution in this case. So that's equal to 2 theta. And keep in mind, n is supposed to be some sort of integer value. So then that means theta is going to be equal to pi over 2n. So the first value of theta is going to be when n is equal to 0 because theta is then equal to 0. So r is equal to 0 then. So that's where we're going to begin, right? So r is equal to 0. And then the next value of n, well, that's when n is equal to 1 because that then gives us theta is equal to pi over 2, okay? So those are going to be my 2 positions then, okay? So as we rotate, when we get to 90 degrees, we're going to rotate back into where the radius is equal to 0. Well, then that means we have everything then. So the area is equal to 1/2 multiplied by the integral from 0 to pi over 2 for 90 degrees. And then r, which we replace by that equation. So that's going to be equal to 4 times the sine of 2 theta then. Okay, and then quantity squared d theta. So once again, this is one of those that you definitely can solve for by hand, but I'm just going to go ahead and say we're going to stop right here for the sake of, just wanting to cover the material. Okay. All right, so there's the setup. Now let's go ahead and look at something even more complex than that. Let's say this time around, I need you to set up again, okay? Set up but do not evaluate the area that is going to be in between the curve. R is equal to 4, and also R is equal to 4 plus 4 cosine of theta. So on the right-hand side, you can see that those are the 2 curves that are there, okay? And I want to find the area of the region that is bounded in between the 2, okay? So that's the blue part that you can see. Now, thinking back to calculus, the second, the how to find the area in between curves. Usually in calculus, we say, hey, the area in between the two curves is the integral from a to b of the upper function minus the lower function, and then we have dx. So that is normal calculus then. In this calculus with the polar, it's the same idea. It's going to be the outer function minus the inner function. Well, I'm sorry. I should be a little bit more specific. It's the outer radius minus the inner radius, okay? And the reason why I have to say inner and outer radius versus function is, well, here, if I create a wedge, just so you can see the partitions, right? I want to find out the area of the blue. Well, now you can kind of clearly see that it's going to be the bigger wedge minus the smaller wedge. Okay, so here is going to be my setup. Then it's going to be the bigger area minus the smaller area. All right. So then that means it's going to be something in the form of what we just did. The outer equation we're given as r is equal to 4 plus 4 cosine of theta. Okay, and then the inner equation is going to be this guy, which is r is equal to 4. Now, this is going to be where it's a little strange because if you recall, again, back in calculus, we had a situation where if you want to find the area in between curves, and then the two are going to overlap like this right here. If I want to find the area in between the two curves like this, where this is y2 and then this is y1, we actually have to break it into two parts, and because the upper bound and the lower bound is going to change. And that's exactly what's happening in this case. If you notice in quadrant 2, you can see that when I draw this little portion over here, your outer equation is now going to be the circle, and your inner equation is going to be the limosone. So that means we're going to have to break this into two parts. All right, so first, let's do the following. First, I need to find out where they intersect each other. So that is to say, I need to know what is this point over here. What is the theta value? So the best thing is I'm going to go ahead and set the two equations equal to each other, but you can probably see that it's going to be it's going to be pi over 2 then, okay? So just, for the sake of algebra, so 4 is equal to 4 plus 4 cosine of theta. So let's see, 0 is equal to 4 cosine of theta. So yeah, theta is definitely equal to pi over 2. Now, that means that my first setup is the following then. The area of that blue piece that's over here in quadrant 1, okay, let's go ahead and say that that's going to be, just A for right now. The area of A is going to be equal to 1/2 multiplied by the integral from 0 to pi over 2. The bigger circle minus the smaller circle area, right? So that means it's the bigger circle in terms of what's the area. It's going to be 4 plus 4 cosine of theta, quantity squared, and then minus the area of the smaller circle. Well, that one is going to be 4 squared, and that is going to be multiplied then by d theta. Okay, so that's the area of that portion that's in quadrant 1. The one that's in quadrant 2, well, if you go to this part right here where I'm solving for cosine, let's see. For this one, if you're going to set up quadrant 2, the blue part, the green portion of it, let's go ahead and call that another name for it. So let's go ahead and call that B right there. Okay. The area of B is going to be 1/2, and then it's going to be the integral. That's going to be in the second quadrant. So it looks like we're going to continue from pi over 2 all the way to, looks like it's going to be equal to pi when they both go back to the center. Because remember, my rotation in quadrant 2 is going to be this piece right here. So from pi over 2 to pi. And then now we're going to set up the area then of the upper minus the lower then. So the outer function is going to be the circle once again. So that's going to be 4 squared minus the inner function squared. So that's going to be 4 plus 4 cosine of theta, quantity squared, and then d theta. So there it is. That's going to be the area of the one in quadrant 1. And then this is going to be the area of the one in quadrant 2. If I want the total area, then that means that I am going to take twice of each one and then add it together. So the total area, okay, is going to be equal to 2a plus 2b. And be very careful, since we're finding the area in between curves, then that means that the upper region, quadrant 1 and quadrant 2, does not cancel out with the lower region of quadrant 3 and quadrant 4. Literally, the thing is to actually double it because I'm looking for the area between curves then, okay? All right, so there you go. That's going to be the area then between two curves. Okay, now let's talk about this last piece right here. Find the length of the petal for the curve r is equal to 4 sine 2 theta. So over here on the right hand side, you can see I have the curve of the petals. I have the equation of the petal, and what I want to do is I want to find the length of this curve that is over here. And then if you want the total, you can multiply everything by 4 then, okay? Okay, so let's think about arc length first, okay? We do remember that for arc length, we did derive it a while back. The area of, the length of curve is supposed to be the integral from a to b of the square root of dx quantity squared plus dy quantity squared. And then we also have on the outside d something. Actually, I guess I should write the parametric then form of this, just so that we can look. It can look a little bit more familiar. We said dx dt quantity squared plus dy dt quantity squared, and then multiply by dt. So right there, that's going to be our parametric equation. I want to take this and convert it into polar. So we're going to see how that works out. So first off, let's go ahead and instead of like saying t, we're going to go ahead and say theta. So that means that the length that we're looking for is still the integral from a to b. But in the inside right here, I'm going to go ahead and write dx d theta because theta is what we're dealing with, right? And then plus dy d theta over here, and that's going to be quantity squared also. And then we have theta on the outside. So if I know what dx d theta is and dy d theta is, then we're pretty much all free. And we actually do know because if you recall, going back to the very first question, we actually did solve for it over here, right? dy d theta and dx d theta. So I can actually make a substitution over here. Now, just to save a little bit of work, over here, if you can look underneath over here, you'll recall that dx d theta is supposed to be this equation, and then dy d theta is supposed to be this equation. So what I want to solve for is kind of like the Pythagorean theorem setup of it. I want dx d theta squared plus dy d theta squared. I did for work for you, so I'm going to go ahead and square the first term on the right, and then square the first term on the right over here, and then add them all up. And it turns out that there are a lot of terms that are going to cancel out. So that is going to be the result over here. To be a little bit more specific, you'll notice that the middle term right here is the same as the middle term right here, so they can cancel each other out. And the first term for each one, they both contains dr d theta squared, and then cosine squared sine squared. So that right there comes out to be just dr divided by d theta squared because cosine squared plus sine squared is equal to 1. And similarly, we have r squared times sine squared plus r squared times cosine squared. So that just comes out to be r squared because, again, the identity then. So in short, what we're trying to solve for on the inside comes out to be just as simple as this right here. So now we can go ahead and write it out. So then L, which is going to be the length of the curve once again, is going to be the integral of the square root of dr d theta, okay, dr d theta quantity squared plus r squared and then d theta, and the boundary is going to be from a to b. Well, I think we have everything then that we need then numerically. So the length that we're solving for is going to be equal to the integral. Again, where does it go from one petal to the again, where does it go in terms of theta? Well, we're going to start from the origin, and we're going to rotate all the way around to this part, going back. So that, to me, is supposed to be from 0 to pi, pi over 2 from last time. And then we have the square root of dr d theta. Well, the derivative of r with respect to theta, that is going to be 4 multiplied by 2, and then cosine. So it looks like it's going to be 8 multiplied by the cosine of 2 theta, and then that whole thing is going to be squared. And then plus r squared, so that's going to be equal to 16 multiplied by the sine squared of 2 theta. Okay, and then we also have d theta on the outside. I guess if we clean this up, the first term right here, let's go ahead and make that a little bit nicer. 8 squared, that becomes 64. And then cosine squared, we'll just go ahead and write that as cosine squared then. But unfortunately, because one is 64 and the other one is 16, we can't combine them together. So in terms of deriving it or solving for it, this is as far as we can go unless we have some sort of technologies to solve for it. All right, well, there you go. Thank you so much for watching all this time. It was fun creating all these video, and I will see you hopefully, sometime in the future then. Okay, all right, have a good one. Bye-bye.